Well, today we have another exciting topic for you. Today we're going to talk about definite integrals, and we're specifically going to be looking at this geometrically. So we're going to go ahead and get started. We have a lot to get through. Please make sure you're taking excellent notes. Okay, first of all, I just want to highlight the difference between indefinite integrals versus definite integrals. So indefinite integrals are what we dealt with last time. If you notice, we just have the integral symbol here, and then we have the function, and then dx, and of course the variable of integration matches the variable of our function. So that's what we dealt with last time. Versus definite integrals, where you can notice you all of a sudden have these new letters. Okay, those are called our bounds. And bounds are very important for definite integrals. They give us a beginning and an ending place. So the way that this is read is we say that this is the integral from a to b of f of x dx. Okay, what this tells us is that we are integrating over a very specific boundary, and that would be from A to B. We want to make sure that when we say that, we are saying it that way, that our lower number, also called the lower bound, is mentioned first. So we say from A to B of the function dx. Okay, so I just said that A is called the lower bound, and B is our upper bound. Okay, so we're going to start working with some integrals of area. And basically, our objective is very important that we understand that we are being asked to find the area between the curve and the x-axis. So when you think of finding an integral geometrically, okay, or not, it's always using the concept of area. And it's specifically between the curve and the x-axis. Always want to go from the curve to the x-axis. Above the x-axis is going to be a positive area. So any curve, any area that we count that's above, it's going to be positive. Any place that the curve dips below the x-axis, we're going to call that a negative area, so a negative answer. All right, so we're going to start off with some pretty basic ones here. And the idea is that we're going to work with today is we're dealing with geometrically, so we are actually going to sketch a graph of what we're given. So we're asked in this first one to find the integral from 1 to 3 of 4 dx. Well, the function f of x equals 4 is a line. Okay, of course we know that it is a horizontal line drawn like that. All right, so what this is asking us to do, these are our bounds from 1 to 3. That is the boundaries in which we want to find the area between. So we're only looking between 1 and 3. And so I'm just going to kind of highlight that area in, and you should be doing the same thing. So this shaded region between the curve, which happens to be our line y equals 4, and the x-axis is what shape? Hopefully you're all saying, oh, that's a rectangle. And so I know the formula for area of a rectangle is just length times width. So I need to know my length, which here is 2, and my width, or my height, is 4. And so I would say that the area here, or the answer, is 8. Remember, all you're doing is calculating the area that's enclosed between your bounds and the curve and the x-axis. All right, let's try another one. So the second one here is from the integral from 0 to 3 of x plus 2 dx. So everyone hopefully should know that x plus 2 is a line crossing through the y-axis at 2 with a slope of 1. So we have a line looking like this. And specifically, we are finding the area between 0 and 2. Okay, so that is the region that I'm trying to find. If you take a look at that shape, hopefully you're seeing that that is the shape of a trapezoid. And so we need to remember the formula for the area of a trapezoid. Area of a trapezoid is 1/2 height, base 1 plus base 2. Okay, well in this case, your trapezoid is kind of sitting on its side. We're used to trapezoids where the parallel sides are the top and bottom of our trapezoid. Remember, our parallel sides are our bases. And so in this case, our parallel sides are in fact the left and the right hand bounds. Those are your parallel sides, those are your base 1 and base 2. Your height is what it's sitting on. And so as we figure this out, we want to make sure to be careful to fill that in correctly. Okay, so we'd say half. We just said the height is what it's sitting on, which is 2. Now we need to figure out our base 1 and our base 2. Our base 1 is very easy because it's between 0 and the y-intercept, which was 2, plus. Now our base 2. Well, after 2 units, how high has this gone up to? Well, don't trust my sketch here. It doesn't look like it's very accurate, but I know my slope, of course, is 1. And so that means every time I go over one x value, my graph has gone up 1 y value. And so for over 2 x values, I need to be going up 2 y values. So this technically is up to 4. So this is the point 2, 4 here. So I can say that I have a height of 4. All right, so then it's just a matter of calculating this. So half of 2 is obviously 1 times 6 is 6. And so the integral from 0 to 3 of x plus 2 dx is equal to 6. Okay, let's try a couple more of this type. So the next one says the integral from negative 2 to 2 of the square root of 4 minus x squared dx. All right, this one might puzzle you for a little bit. What is that shape all about? Well, I'm just going to kind of pull the function out and write it as y equals the square root of 4 minus x squared. All right, and now I just want to see what this is. And so I want to get rid of that square root, so I'm going to go ahead and square both sides. And I'd have y squared equals 4 minus x squared. Now what happens if you go ahead and bring your x squared and y squared together? You have x squared plus y squared equals 4. Now hopefully something is ringing in your brain and you say, oh, I know, that's a circle with a radius of 2, because it's the square root, of course, of this number, and a center of 0, 0. So you should recognize that formula. Now that I've kind of brought this to your attention, I want you to recognize that when you are given a function in this form, you shouldn't have to go through this whole process. When you're given a function in this form, you know that this is in fact really just half of a circle. Why just half? Well, because if you look here, this was the positive square root of this function. Okay, it wasn't the negative. And so what it does is it just takes the top half. If I were to take the square root and have plus and minus, then I would have the top and bottom. If I just had negative square root of 4 minus x squared, I would have the bottom half. Okay, and so here I have a picture that looks like this. I'm going from negative 2 to 2, and I just said it's a semicircle with a radius of 2 and a centered at the origin. And so I'm looking at a half circle or a semicircle that looks like that. And if you look at my integral, I am asked to integrate between the bounds of negative 2 and 2. So specifically from here to here, so this whole region under the curve, which we just said is a semicircle. And so again, now let's pull out our formula for area of a circle. We should know is pi r squared. Half of that, since we're only talking about half of the circle, is half pi r squared. And so we can go ahead and fill this in as half pi times 2 squared, which would be half of 4, so 2 pi. And we can leave it in terms of pi is the integral from negative 2 to 2 of square root 4 minus x squared dx. All right, last one we're going to do of this type is the integral from negative 1 to 1 of x dx. Okay, so back to what we were talking about with the first couple. We're just looking at the equation of a line, y equals x. And we should know that this is your perfectly diagonal. It passes through the points 1, 1, 2, 2, 3, 3, and so on. And this time we are looking at it from negative 1 to 1. So we are looking from here to here as I draw in my bounds. You can see that I have this triangle below the x-axis and this triangle above the x-axis. I want you to think for a second. What do we know about, first of all, what did I say about what happens when you're looking at the area below the x-axis? And hopefully you remember it's negative. And then what do we know about these two areas? Well, I would say that both of them are triangles with the same base, a base of 1 and a height of 1. And so both of them are congruent triangles. Well, if this one is negative and if the left-hand one here is negative and this one is positive, what I would say is that they cancel each other out and my integral from -1 to 1 is in fact 0. So this is kind of a cool phenomenon that happens, and you want to watch for it because it's going to simplify your problems. So if you look to the left and to the right and you are noticing that you have areas that are identical in size, they are congruent shapes above and below, and one is below and one is above, they're going to cancel each other out and you're going to get an area of 0. There are several properties of definite integrals that you want to get into your notebook. We're going to use these, and they are fairly straightforward and very easy to understand, but we definitely want to get them down so that you are able to use them. And over on the right-hand side here, I just have a general integral picture from A to B, the area under the curve of f of x. And so we're just kind of looking at that to help us understand these different properties. The first one is called the multiplication by a constant. K is your constant. And so as I look at this, all right, I have the integral from A to B of K times f of x dx. All this is saying is that that constant can come out in front, and so it's K times the integral from A to B of f of x dx. So that just tells you if you have a constant, pull it out in front, and then do the integral and multiply times your constant at the end. Okay, negation. This one comes up quite a bit. What this is saying is that the integral from A to B of f of x dx is equal to the negative of the integral from B to A of f of x dx. So if your bounds, as we usually see them, our bounds are from the smaller number to the bigger number, where A is smaller than B. Well, if it happens that they reverse that and they put the larger number on the bottom to the smaller number, well, if I want to find that integral, I just can flip it around and negate it. Okay, so we're going to practice that one quite a bit. Decomposition. This is only true if A is smaller than C, which is smaller than B. So in other words, C has to be between A and B. Okay, the integral from A to B, f of x dx, is equal to the integral from A to C, f of x dx, plus the integral from C to B, f of x dx. So this is just telling you, for example, on our picture here, if I had a value C right here, that the integral from A to B, the whole integral, the whole area under the curve, is equal to, I could split it up and say I could find the area from A to C, if that would be easier, and add it to the area from C to B. And that would be the same as just finding the area all the way from A to B. So pretty straightforward, and again, common sense should make sense to you. Okay, the next one says it's the addition one. And we actually could say addition or subtraction. So I can go ahead and put a plus or a minus here, and a plus or a minus here. Okay, so what this is saying is that the sum of two functions and their integral from A to B is equal to the integral of A to B of f of x dx plus the integral of from A to B of g of x dx. And the same is true for the difference. So again, it's splitting it up, and you could do the integral of each piece and then put them together for the total sum. Okay, the zero integral. Now this one, if you look at our picture, this one should make a lot of sense. It's saying the integral from A to A of f of x dx is 0. Well, if you look at A here, if I go and I say I want to find the area in the space between A and A, well, hopefully you're realizing there is no space between A and A because A is the identical same number. And so therefore it makes sense that the area that is trapped between A and A would be 0. Okay, we're going to try a few examples using these properties. And what you have here is a graph of f, And they have already highlighted for you the areas under the curve. So they're saying that the area here between A and B is 3. The area here between B and C is 1, between C and D is 2, and between D and E is 5. So they're giving you those areas that is trapped in that curve between the curve and the x-axis. Okay, so we're going to go ahead and evaluate these, again, stressing our new properties that we just learned. So the integral from a to a of f of x dx is, well, what do we just say? If I went from a to a, there is no area covered, it's 0. Okay, the next one, the integral from a to c of 4 times f of x dx. Okay, well, first of all, I'm going to pull that constant out. So I have 4 times the integral of a to c of f of x dx. Now, if I look at the area between A and C, I notice that I have two different curves, two different areas that I have to consider. So I could split this up even further if I wanted to, just to highlight the point, and say that this is 4 times the integral from A to B of f of x dx plus the integral from B to C of f of x dx. And now, if I go ahead and find each of those pieces, I'm going to be able to find my answer. So the integral from a to b of f of x dx, we can clearly see is 3. Now, the integral from b to c of f of x dx is, it looks like it's 1, but keep in mind, if that curve dips below the x-axis, we are going to say that that is a negative answer. So we're going to go ahead and say that that's -1. So my total area, my total answer here, my integral, would be 4 times, looks like 3 plus -1 is 2, so my answer is going to be 8. All right, let's try letter C here. The integral from D to A of f of x dx. All right, so I'm going to squeeze C in right here. All right, first of all, if I look and I say the integral from, notice what I said. I said the integral from D, which is over here, to A, which is over here. What do you notice? That's in the backwards order. We always read from left to right. If they give us an integral where the lower bound is further to the right on the x-axis than the upper bound, then we need to flip that around. So I'm going to rewrite this as the integral from the negative of the integral from a to d of f of x dx. And this time I'm just going to kind of figure it out. I'm not going to break it up like I did last time. So I know my answer is going to be negative of whatever I find. All right, so from A to D, well, I have, what are my positive areas? I would definitely say that my positive areas would be between A and B would be 3, and between C and D would be 2. So that would be 5. And then I'm going to take away my negative area of 1, so -1. So 5 minus 1 is 4. Negative of that is -4 is my answer for letter C. Okay, I cleared that off, so I have a little bit of room to do letter D here. Letter D says the integral from A to E of the absolute value of f of x dx. Okay, let's think about what absolute value means. Absolute value means, of course, make it positive. So what it's asking us to do is take the graph of f of x and make sure it's positive. So this part of the graph that's dipped below between B and C and between D and E, they want us to bring it up to positive. So that means I'm looking at positive areas of 1 and 5 instead of negative. So now I can tell that my total area is going to be the sum of all of these. So that would be 3 plus 1 plus 2 plus 5, which of course is 11. Okay, in this next example, we're looking at a new graph of function g, and I want you to take a few minutes to accurately sketch it into your notebook. Please take your time and make sure that it is accurately sketched and that you have the right heights and things like that. Okay, so we're going to go ahead and start evaluating. Pause the video and sketch it in if you need to, and then come back to us. All right, number 1 is the integral from -2 to 2 of g of x dx. So area under the curve from -2 to 2 of g of x dx. All right, so take a look. I'm looking between -2 and 2. Well, clearly that to me is a semicircle. And so I'm going to go ahead and say that my area is 1/2 pi times my radius squared, which here I can tell my radius is 2 squared. So that would be half of 4 pi is 2 pi is my answer. All right, pretty easy one to start off with. Number 2, the integral from -9 to -4. So I'm looking at this and this. Okay, so I can see that those are two triangles, and I can see that one of them, specifically this one here, is dipped below the x-axis, and this one here is above the x-axis. So I'm going to have one negative and one positive that I'm adding together. All right, so I have the integral, of course I'm going to break this up, the integral from -9 to -6 of g of x dx, plus the integral from -6 to -4 of g of x dx. That's that decomposition property. All right, so this first one we said we know is going to be a negative answer, so I'm going to mark it negative right away. All right, now I would say that the area of a triangle is 1/2 base times height. My base here is 3 and my height is 2. So 1/2 of 3 times 2. Okay, plus the integral from -6 to 4. So if I look at this triangle, it's again 1/2 times base times height. This time I have a base of 2 and a height of 3. So what are we recognizing? This is another one of those cases where the triangle at the left and the triangle at the right are identical. And you can see what happens, that we are going to go ahead and those are going to cancel out, and we're going to get a final answer of 0. All right, let's move on and look at number 3. This time I'm looking from 0 to 5, the integral from 0 to 5. Okay, so I have just this much of the semicircle and then this triangle down below. All right, so obviously if I have half of a semicircle, we're talking about a quarter circle. So the integral, again, I could break this up and say the integral from 0 to 2 g of x dx plus the integral from 2 to 5 g of x dx. All right, so from 0 to 2 we said that was a quarter circle. So we were looking at pi r squared divided by 4. So pi times 2 squared, which of course was 4, divided by 4. Plus the integral from 2 to 5 is a triangle. So we have 1/2 times the base times the height. Well, our base here is 3. And our height is 4. Now, again, that is below the x-axis. That triangle is dipped below the x-axis, so I would say that that is negative. All right, so my answer here is going to be just pi minus, let's see, half of 12 would be 6. So pi minus 6 is my integral answer. Okay, the last one we're going to look at is the integral from 9 to 5. So from 9 to 5, and hopefully as soon as I'm saying that, you're going, wait a second, that's backwards. That is not from left to right, that is from right to left. And so right away, you hopefully are saying, I'm going to go ahead and reverse those bounds and say it's from 5 to 9 of g of x dx. But of course that means I have to make it negative. But then I want to look at what part of where I did my highlighting. And hopefully you'll say, oh wait, that's below the x-axis. So that's also negative. So we're looking at a double negative situation because what we're saying is whatever this answer is, we have to make negative. And of course we know that the negative of a negative is a positive. So really these are going to cancel each other out. And so now we're ready to go ahead and find the area. Hopefully you recognize that this is the shape of a trapezoid again. With the trapezoid, we want to identify our parallel sides as our bases. This time our top and our bottom are our bases, and our height is the left-hand side there. Okay, so we're going to go ahead and use the trapezoid formula, which we know is half, times the height, which we just identified as 4, times base 1 plus base 2. All right, I'm going to say the bottom base is 2, plus my top base is 4. So I have half of 4 is 2. 2 times 6 is 12. And so my integral answer is 12. Ladies and gentlemen, in general, these kind of questions are extremely prevalent on the AP exam. Almost every single AP exam has one of these as a short answer question, where you have to do part of this is to find these area under the curve. And so this is a huge concept of the AP, so we're going to practice this a lot, but I hope that you understand it. Please, if not, if you're confused, go back and redo a few more. We're going to move into a couple more examples that are very common multiple choice, where we take the graphs away, but we're just more looking at the rules. So let's get into those. Okay, these go pretty quick. We're given 3 integral rules and their values up here. So we're told that the integral from 1 to 2 of some function f of x dx is equal to -4. We're also given that the integral from 1 to 5 of the same function f of x dx is 6. And the integral from 1 to 5 of the integral of a different function, g of x dx, is equal to 8. And we're asked to find each integral. So these go pretty quick, and we just want to kind of use common sense and our properties. So the first one is the integral from 2 to 2 of g of x dx. Well, I don't even have to look at any of those 3 rules. I recognize that I have the same lower and upper bound, and I know that that answer is going to be 0. All right, letter B. So I recognize that these were the same. Letter B, the integral from 5 to 1 of g of x dx. Okay, again, another property should be jumping out at me. I'm looking here and I'm noticing that I go from 5 to 1, but the rule that was given was from 1 to 5. So I'm going to go ahead and rewrite this as the negative integral from 1 to 5 of g of x dx. And now I would say it's negative of 8. So -8 is your answer for letter B. Okay, letter C, the integral from 1 to 2 of 3 times f of x dx. Once again, using one of your property rules, this is the constant multiplication. So I'm going to rewrite this where I pull my constant 3 out in front, 3 times the integral from 1 to 2 of f of x dx. So it's simply 3 times -4, which of course is -12. Okay, really straightforward on those first 3. Let's go ahead and tackle letter D. All right. The integral from 2 to 5 of f of x dx. I want you to look at our 2 values that were given, the 2 integrals that deal with the function f of x. The first one we're given is the integral from 1 to 2 of f of x dx, and the second one is from 1 to 5. And the question we're asked is from 2 to 5 of f of x dx. So these were actually asked most common on the AP compared to all of these. And the idea is that we want to recognize that there is an overlap. Okay, that this first integral here is from 1 to 2, but this is all the way from 1 to 5. And they only want it from 2 to 5. So hopefully you're saying, well, what I need to do is cut off, take away the overlap. So if I were to take away the integral from 1 to 2, away from the integral from 1 to 5, I would be left with 2 to 5. And that's exactly what we're going to do. We are going to go ahead and subtract. We're going to take the integral, the integral from 1 to 5 of f of x dx, and we're going to subtract away the integral from 1 to 2 of f of x dx. And what we'd be left with, of course, would be the integral from 2 to 5. We're subtracting that value away. So I'm just going to fill in now my values. It would be 6 minus -4, which of course is 10. And that's it. It's just this idea of understanding this overlap and subtracting that overlap away. Okay, we have one more set of these examples, so go ahead and get these copied down. Again, we're talking about 2 different functions, f and g. They're continuous functions, and we're given these 3 different integral values. Actually, it should be f and h, I guess we're talking about here. So the integral from 1 to 9 of f of x dx is -1. The integral from 7 to 9 of f of x dx is 5. And the integral from 7 to 9 of h of x dx is 4. All right, so what I want you to do actually is go ahead and pause the video. Try these on your own. They're not too hard at all. I think that you can do them, and come back to me and see if you got the right answers. Okay, welcome back. So let's take a look at your answers and quickly just scan and see if you got them right. Letter A was just using that constant multiple rule, so we pulled the -2 out, and I evaluated that and got a +2. Letter B was using my addition kind of pull apart rule. So I evaluated the integral from 7 to 9 of f of x dx and the integral from 7 to 9 of h of x dx and added those together and got 9. Letter C, this is the one that I said comes up the most frequently. Okay, so this is that overlap one. I'm looking for the integral just from 1 to 7. Well, none of these were given from 1 to 7 of f of x. But the two f of x ones that I were given were from 1 to 9 and 7 to 9. I know that if I took the integral from 1 to 9 and kind of chopped off the 7 to 9, I'd be left with just 1 to 7. And that's exactly what I did. I took the 1 to 9, I subtracted away the integral of 7 to 9, and I'm left just with then the integral from 1 to 7, which is -6. The last one here is letter D, and that's from 7 to 9. And the integral was 2 times f of x minus 3 times h of x dx. So again, we had a multiple rule in there and a subtraction rule. So I pulled that all apart, pulled out my multiples, and evaluated it and got an answer of -2. All right, thanks a lot, guys. Thanks for sticking with me. Again, I cannot stress enough how frequently all of these types of questions come up in the exam, and we will not be done with them, but this is a huge, very important lesson. So I really hope you took good notes, and I'll be looking forward to seeing you in class next time. Thanks so much.